I ran an experiment to explore the differences in ColBERT indexing and retrieval between FP32 full precision and mixed precision. So in this video, I'm going to walk through how I approached it and what the results were. So the first thing I did is I created a new branch in a fork of the ColBERT repo. So I call it mixed precision false. And there were a number of files that I edited to make sure that everything was in full precision. The way that I approached this was I gave my fork and branch to Claude, and I used Opus in a couple of conversations, and I said, hey, I've attached this branch. I'm trying to turn off all half precision conversions. I want to make sure everything's in full precision. Can you look through it and let me know what you find and where I should edit things? And so I found a bunch of things on my own, but there were definitely a lot of details that Claude found. For example, in this decompressed residuals CUDA kernel, where I had to change a bunch of the half precision items to full precision float values. So that was kind of my initial attempt at making sure everything was in full precision. So I'm going to walk through those changes. So in the modeling checkpoint.py, there's a mixed precision manager, which is set to true. So I made sure I set that to false. And that was, I think, one of the first changes I made, which is that's why I called this branch mixed precision false. Then inside the ColBERT modeling file itself, inside the doc method, when it actually gets the embeddings from BERT, if it's using GPU, it converts it to half. And so I commented that out. A couple other spots. Here it's encoding passages, so it's getting embeddings, converting those to float 16. So I commented that part out. Here, when it saves the sample embeddings, it saves it in half precision. So I saved that in full precision. In the concatenate and split sample method, when it gets the sample, it instantiates that tensor as float 16, so I changed that to float 32. The centroids are in half precision, so I changed that to float. When it's actually doing the residual calculations, it sets the batch to half precision, so I changed that to float. It's when it does the cosine similarity between centroids and the embeddings, it does half precision, so I set that to float. Saving the centroids, I made sure that it's full precision. Now we get into CUDA kernels, which I understand not that great, so I relied on Claude and ChatGPT. So I changed this kfloat 16 to kfloat 32. The queries, make sure those during retrieval are in full precision. A bunch of other items in the CUDA kernel which I went from @half to float. And then even though I've already set the mixed precision manager to false in the config, I made sure that default value was false. And then just for completeness, even in the training file, even though I'm not training anything and it's not going to affect that, change that to false as well. So that was my approach of making sure everything is in full precision to the best of my knowledge. I understand that this is not ideal for GPUs, and I don't understand that very well. It's just something I've heard and read, that when you're using a GPU, you want to use half precision because it handles that better. I don't know the details on that. So I'm not doing this as a best practice. This is just a curiosity exploration that I'm pursuing. So what I did is I created two environments. In Conda, I had one environment where I'm loading the usual ColBERT, and then I had one environment where I was loading the mixed precision false branch, so the full precision ColBERT. And then basically I ran two different files. One is I did the indexing and I was tracking memory, and then in a separate file, separate script, I calculated the recall. So I'm going to walk through those files here. The first one is called ColBERT memplot, and here I am using a separate thread to calculate the memory or log the memory every 5 seconds. And so here this memory monitor is getting the CPU memory in gigabytes, and it's getting the GPU memory, and then it's appending it to these lists. And that's happening while my indexing code is running. So here's the config that I used. This is just something I picked up from a previous experiment. There's nothing really specific that I tried here. These are just some values. And then I'm actually running the indexer.index path. The dataset that I'm using is the UKPLabs CAPR's conditional QA dataset. So that's where I'm getting these passages. Everything in the main function is pretty standard. I have an argument parser, so I can pass the precision type. So this is actually FP, doesn't really make sense, but I guess it does, floating point. So yeah, either FP32 for full precision or AMP for mixed precision. I'm loading the data set, I'm running the indexing, and then this is code just to save the data for CPU and GPU readings, as well as create a plot, which we'll look at in a second. So I ran these from the command line from the different environments so that it was using the different ColBERT implementations, so full precision and the mixed precision. And then I have this recall file script, pretty standard stuff. The kernels have to be a dictionary in this format for PyTrek eval. You create an evaluator, you give it your results, and it calculates the metrics, and then I get the mean recall. I'm loading the data set, setting up the kernels. ColBERT wants a dictionary for its queries, so I'm setting that up. And then the key thing here is I'm getting the index path. So I have this argument called index, where I get the index name. So in the environment that has full precision, I'm passing it the full precision index. And in the environment that I've created where I have mixed precision, I'm passing it the mixed precision index. And so everything else is pretty standard. Just using some values that I've used before. For the searcher, I get the ranking, prepare the results in a way that PyTrek eval expects it, save the results so I can analyze it, and then I print the recall. So those are my two scripts. First thing is we'll look at the memory readings first. So here's full precision GPU readings. And interestingly, this took 70 seconds and the maximum reading was 5.5 gigabytes. If we look at the mixed precision GPU readings, this took 180 seconds and the max memory was 5.78. So I was not expecting that. I was expecting the full precision approach to use up more memory. So I don't really know what's going on there. Maybe the data set was small enough where it didn't matter, and these are just negligible differences. The conditional QA dataset is 70,000 rows. And then the CPU readings, the maximum memory for full precision was 0.8235. For mixed precision, it was a bit less at 0.814, so it did use less CPU memory. And again, I was surprised to see that full precision took 70 seconds, mixed precision took 180 seconds. Yeah, so that's kind of noteworthy. Again, not really sure. I haven't done like full memory profiling, so can't show where the differences are exactly. And if we look at some of our plots, here's the GPU RAM for full precision, and then here is the GPU RAM for mixed precision. So there is a difference in how this memory is being used. The mixed precision has this kind of plateau here. Full precision doesn't have as much of a plateau. And maybe there's some difference here in terms of processing, and maybe this is why this mixed precision took 100 seconds longer. And then if we look at our CPU readings, here's the full precision. It spikes up here at like 8.83. And if we look at mixed precision, it spikes a little just shy of 0.82, and then it levels out. So yeah, interesting differences. The biggest difference is time, and I'm not sure why it takes longer for the mixed precision to index. So that was the first part of the comparison. I wanted to see what was the difference during the process of indexing. The second part of the comparison is looking at what are the differences after indexing during retrieval. So if you calculate the recall with each of these different environments, full precision and mixed precision, the difference is very, very small. It's 0.3%. It's give you a slightly larger recall. I mean, at this point, it's pretty negligible, 0.129938 versus 0.130348, so on. So Not a big difference, but the indexing was faster, so you get better recall and it takes less time. The next thing I did is I wanted to look at, do these different approaches retrieve the same passages? And the answer is that they do not. So this is what one of the retrieved items looks like. So this is for the query ID dev-0, and it has a dictionary where this is the passage ID, and then this is the score that was calculated during the plaid scoring pipeline during retrieval. And for each of these items, we have 10 passages that were retrieved. So I looked at, in each dictionary, the full precision dictionary, as well as the mixed precision dictionary. I looked at every query ID, and then in that query ID dictionary of 10 retrieved passages, I looked at each passage ID, and if the passage ID in one of the results was not in the other one, then I counted that as a difference. And so here I'm looking at my full precision items, and if the passages that were retrieved are not in the mixed precision items, then it adds 1 to this ndifs counter. And then for my mixed precision items, if the passage for those 10 passages for each query ID, if it's not in my full precision items, I add that to my ndifs as well. So I'm checking both directions. And this was interesting to see. So out of the about 3,000 retrieved passages, 388 were different across the two approaches, which is about 14%. So it was interesting to see that changing the precision level not only affects the indexing process, but it also affects the outcome in terms of the passages that are actually retrieved. And we'll see exactly why later on, or at least one potential explanation for why it has this different number of retrieved passages. The next thing I checked was the score. So I was assuming maybe the full precision retrieval, maybe it has a higher score. That was kind of my initial guess. Turns out that I was wrong. The mixed precision score is actually slightly higher. So I'm looking through each of the 10 passages for each query, and I'm just adding up the score. So 29.345 plus 29.341, etc. And the total score for mixed precision is 80,438, whereas the total score for full precision is 80,435. So full precision actually has a slightly lower score. And then the final comparison I've done is I've compared the index artifacts. So here's my full precision index, and here is my mixed precision index. And again, these were created in two different environments with two different ColBERT branches installed. I'm looking at the metadata, and I'm looking at things like the number of bits, the k-means iterations, the number of GPUs, the number of chunks, the number of centroids, the number of embeddings, and so on. And all of that was actually the same. So if you look through the metadata values, those two match. But now we start seeing some differentiation when we look at the centroids and when we look at the actual mapping between passage IDs and centroids. So centroids.dt, the actual I think it's 8,000 or so centroids that are the result of the clustering of different document token embeddings. And here we have to change the precision to use all close. So here we have the full precision centroids, and here we have the mixed precision centroids. So I here change the mixed precision to full precision, and using the default tolerance, the centroids are not similar. And then I do the other direction as well. I change my full precision to half precision, and still the default tolerance is not cleared. It actually takes a ridiculously large tolerance for this to give a true result. So I actually have to use a tolerance of 1.0, which obviously, given that these are fractional values, is very large. And then you get true. So effectively, just looking at this, I can say, yeah, these centroids are very different. So full precision and mixed precision centroids are completely different. Well, not completely different, but very different. Both have the same number of items. So that makes sense, because if we go back up here, the number of partitions was equal, and number of partitions is the number of centroids. And they're both using the same ColBERT model, the Answer AI ColBERT model, which has a dimension of 96. So it's using that same dimension for both. This was really cool to see. So I'm actually plotting, I flatten out the centroids for each of my results, and I'm doing a scatter plot between them. And here you can really see like, okay, there is a lot of variance between these two centroids. So this was really cool to see this difference. And the last item I'm going to look at is the actual mapping from passage IDs to centroid IDs. And this is the ivf.pid.pt. So if we look at the IVF, which is the sequence of passage IDs, I can't compare them with Torch all close because there are different number of elements. The full precision actually has 963,000 elements. The mixed precision actually has more with 975,000. So there's about a 12,000 passage ID difference between mixed precision and full precision. And I don't know exactly why that is the case, but what that means is that it's finding more mappings between passage IDs and centroid IDs when you're using mixed precision. And I hesitate to, guess why that's happening. Maybe one explanation could be that document token embeddings that are similar enough between two passages where the mixed precision kind of cancels out any differences, maybe increases the number of comparisons between passage IDs and centroid IDs. I don't really know, but this was definitely interesting to see. And then the second item in IVF PID is the count of passage IDs for each centroid. And here we see that they have the same number of centroids, which is 16,384. So I think overall, there was mixed results in what I experienced. First thing is that mixed precision takes longer to index, and I'm not sure why. Second thing is that, and when it comes to GPU memory, the mixed precision actually takes up a little more memory, which was interesting for me to see. And then when it comes to CPU memory, full precision takes up a little more memory, which makes more sense. You get a very, very slight, basically insignificant boost in recall if you use full precision. You get considerable amount of different passages retrieved if you use full precision. You overall get a lower score for these passages when you're using full precision. And you get a different set of index artifacts. So your centroids are different, and the mapping between passage IDs and centroids are different. So again, this is a sample size of 1. This is just one data set and a relatively small data set with 70,000 documents. And these documents are very small. On average, I think there's like 15 tokens per document. So I hesitate to make any claims about mixed precision and full precision in terms of indexing, in terms of ColBERT. There's also a chance that, how I've made some of these changes is not accurate. Maybe I missed some things, but this was just an exercise. I was just curious. And all I really wanted to see was, is there a difference? And yes, there is. And so that was cool to witness. So that's it for this video. I will either today or tomorrow post a blog post with all of this code in there, so make sure to check that out if you want to recreate these experiments yourself. Make sure to like, comment, subscribe, and I will see you in the next video. Thanks.